So, hello again, everybody, and welcome to the first lecture of our telecommunications theory course. So, in this course, we will talk about telecommunication systems, and this will be our first lecture in which I am going to tell you the general structure of the system which is used to transmit digital information by using a communication system. So we will have this diagram discussed today. By the way, this is actually the diagram which will be the first task of your course project. Yes, so basically your course project, well, actually, I can show you as we have it open from the previous year. I will soon enough provide this file for you because basically I need to assign some these variants to you. Yes, you have, there are a lot of you, and everybody should have, should have a specific set of parameters. I will also assign some parameters to myself to show in examples, yes. But for now, we are interested in the tasks itself, what you will do in this course project. And today we will do the first task, the diagram of digital information transmission system and the description of each of its blocks. Yes, these other tasks will be solved as we go during the course, but for today you can already draw this picture, and this will go into your course project as the first task. Yes, along with description of each separate component. What does it do? Yes. Okay, so we'll start talking about that, but before let us discuss what literature you can use for this course. As I mentioned in the organizational video, yes, you can use all the course materials I provide you, and this will be sufficient for you to actually pass the course to the maximal grade of 9, yes, out of 10. If you desire to get 10 out of 10, then you will need to use some additional information over the internet, over the books, yes, to solve extra tasks. But as far as it goes for the standard program, yes, everything I give you should be sufficient to actually, get graded to the maximum. Yes, you will have lecture slides, you will have course project descriptions, you will have video records, you will have video records from the previous year, and this should be sufficient. But if you need additional information, you can use this very good book on digital communications fundamentals. Yes, and it's written in quite simple language. There is also not too much mathematics, so you can basically understand. Of course, naturally, it's such a big book that covers a lot more than I will be giving you in this course, but it's okay if you are interested in additional material, what we are not discussing in this lecture. So this is a very good book. This is for different modulation types, for different coding schemes. We'll talk about what it is very soon. Yes, today. Another good book is Heikin book, Core Communication Systems. This is not only related to digital systems, yes. As you can see, these books were written quite some time ago, but they are still very good and provide information on some fundamental things, basics, yes, which are based on laws of the nature, on the physics and mathematics. So nothing really changed there. So you can still use these books. I think there should be also third edition maybe, which was issued more recently, but I'm not sure if there is a third edition, yes. And another literature to be recommended is this Telecommunications Essential second edition book. So you may use these books in addition to all the course materials, and you are also welcome to recommend any additional literature if you happen to find good source which helped you, and I will add it for the next year students if they will be so they will be able to use that as well. So this will be for the literature, and let's see what we will be study during this course. So during this course we will cover multiple topics. Yes, first and maybe the most basic one we will discuss today, the general structure of the system for transmitting information. Yes, so we'll talk about what is information, what is system, what are signals, and everything of that at the beginning of this course today in our first lecture. In the first part of our first lecture, some definitions, yes, because we need to understand what is this information, how can we work with it, what we can do, how to transmit it, and so on. So we'll start this course with some definitions, and then we'll discuss the structure of the system which is used for transmitting this information. Now, during this course, it's not only today, but basically over the entire duration of this course, we'll talk about the purpose and operation principles of each of these components, making this entire system. And even so, we'll be, let us say, not into much details for some blocks, for some components. For other components, we will be very detailed and very specific about some details, yes, but these blocks can be different. Well, I will point out that when we are talking, for example, about coding, that we are talking about some particular coding in our course, and that actually there are multiple choices available, some better codes perhaps. So when we will get to those components, I will be definitely mentioning that it can be done in other way than we look in this course. But for this course, we will basically most often take the most simple principles, yes, to understand the basics. And once you understand basics, you will be able to use, for example, Wikipedia or any of the books I provided to learn about more complex problems, yes. So, structure and description of each of the blocks, yes. Next point is quantitative evaluation of information. So this basically means measuring information. Because, for example, you know that for modern internet, we can describe the data transfer rate in, for example, megabits or gigabits per second. And this measure has to somehow be related to the amount of information we send and time it takes to transmit some information. So we'll talk about that as well, how to measure it and what are their, let us say so, fundamental laws, how big it can be for the system, can we grow it indefinitely, for example, can we hope to get 100 gigabits for our home Wi-Fi routers, for example, yes, can we get like 1000 terabits for optical networks? Well, in short answer is it's definitely possible, but this will have some requirements. And we'll talk about what are these requirements that define what is the cap, the limit for the data transfer rate. So we'll talk about that in this course as well. And the last two parts will be related to coding of information. So we will have two types of coding. We will have statistical coding, which will be used for data compression. So, as you can imagine, this is useful if we'd like to minimize the time to transmit the information. The compressed information will be transmitted faster, but accordingly, it will be more vulnerable, more susceptible to some interference, to some problems, errors, and so on. So we'll, for that reason, need additional compression, which will be error correcting codes. Yes, so error checking and correcting. Check or correct. And we'll discuss these codes as well. They will be part of your course project as well. You will have some parameters specified for you, and we'll need to design the code, show examples how it's working, how it corrects the errors. I will show you some simple examples today as well to show you how is it possible and how it works. But overall, this will be left for the last part of our course. And then you will learn it in all the details, all the mathematics behind these, how it's working and allowing to correct information when you receive it with errors. So this is the outline of our course, yes, and we'll stick to it over the entire semester. Let us start, before we go to the structure, let us start with the main concepts. What is what and what is information, how we can measure it, how we can send it, and so on. So let us start with this definition of information. And when we talk with each other in this course, you already have some impression what it might be, this information. Yes, this is some set of facts or events, yes, which we are sharing with each other, yes, recording somewhere in, for example, in history, yes. So this is actually something not material. This is these are some ideas, facts, and so on in a wide sense of definition. It's equivalent to news, yes, on something, and we can write this information. We can type it in our computers or mobile phones. We can record it on some data storage devices. We can then convert this information somehow, yes, transmit it and operate with it. But the question is, if information is something not material, how can we work with it? Yes, because basically this information itself is not something present in our material world. Yes, it's basically, well, for example, if we write it in paper, then we write it in paper with some letters. Yes, and these letters contain some specific information. Furthermore, the order in which we put these letters also contains information, because here letter L has one type of information, and in another word, for example, laser, it has different information. Yes, so we'll talk about that right now. Yes, but before that, I'd like to mention that there is also a technical definition of the information, in addition to some common sense definition. So from a technical point of view, the information is uncertainty. It's a probability. Yes, that you don't know what you are going to receive. So imagine the fact that you are receiving digits from 0 to 9, which are sent to you over some device here and displayed on some screen. And you do not know for certain what will be sent. Each of these digits is sent, let us say, with 10% probability. Yes, so it's completely uncertain what digit will show up next. Yes, and from that point of view, this will be very informative message for you. So let us say you have received 1 and you were completely unaware that this will happen. Yes, so the amount of information this one is providing to you is maximum. Now let us consider that there is another case where the setup is very similar, but you are transmitting only digit 5 all the time. So you will always get 5 with 100% probability. In that case, once you have received 5 for the first time, each next time will give you less and less new information. Yes, so you will be already knowing that the next digit will be 5. However, if something happens because of the error, in the process and you will get, for example, not 5 but 6, this will be a new event which will give you a lot of new information. Although incorrect information, yes, but still this will be a large volume of new information because something unexpected happened. So very similar is with some facts in our life. Then somebody is telling very obvious things to you which you already know. These are not very informative for you. And to the contrary, if you learn something new in from some person, yes, this gives you a lot of new information because basically you didn't know that previously. So this technical definition allows us to actually measure how much new information you get based on the probability of this event, how it's happening. Yes. So this way we are actually sooner or later going to get to the bit measurement unit, which we use constantly in our lives. Yes, when we measure data rates, when we measure information volumes. Well, we do measure information volumes in bytes, but as you know, bytes consist of 8 bits. So anyway, this is let us say, coming from this technical definition of the information. We'll talk about this bit measuring unit a little bit. Well, not actually a little bit, but I think somewhere in the middle of our course, how it happened to occur, yes. But for now, it's sufficient to know that these bits are measurement units of information, and they are basically related to how unexpected is this message, yes. Well, I used the term message before describing what does it mean, but we'll describe it right now, yes? So regardless of what type of the information it is, it's always possible by using this technical definition to describe it in quality and in quantity. So for the quantity, this is actually the amount of information, but for the quality, it's actually if the information has been transmitted correctly. So here, for example, in our last example, when we discussed the error happening during the transmission, the quality shows that instead of expected 5, we have received 6. And this way, it's possible to tell that something incorrect happened because we knew that we should receive 5, but instead we received 6. So it means that the information has been received incorrectly because of different factors, which can be channel problems, yes, which can be system malfunctioning problems, and something else, yes. So basically, qualitative means that we are checking if we received information correctly, and quantitative means that we count how much of information we have received. So this enables us to measure volume of information, so amount of information. Once we know how much information we have, we can send it over a certain time and calculate, yes, so let us say volume of information divided by time will give us the rate. And that's actually how we measure these gigabits or megabits per second, yes. So for giga, we have 10 at the degree of 9 bits per 1 second. So that's basically the amount of information equivalent to this being transmitted over a duration of 1 second. So this is called data rate, yes, transmission rate. And this can be calculated if we know the amount of information which is being sent and the time, how long it took to send this information as well. There will be some theoretical limits to this data rate based on the specific information and so on, but we'll talk about it, of course, not on our first lecture, because the course is quite big and there is also quite enough mathematics involved in this course. So we'll talk about this today in very simple terms, yes. And the quality of information, as I said, whether it matches what should be sent or not. How correct is operation of our communication system, because ideally you should understand that the system which sends information should send it reliably. Yes, so we should receive correct information, and if the system well makes something bad with our information, then this system cannot be really trusted. Yes, and you don't get the information you were meant to get, and this is quite important to assure that the quality of the system is actually good enough. Yes. So let's get to the next definition. We usually work with information in some sort of characters or symbols. Yes, so symbols is some logical structure how we work with information. So in our letters, in our writing, yes, we use with characters such as letters, digits to write down this information on paper or in computer and do something with that. For example, we write books, which can be then put into the library, then some students come for these books, get these books, read them, and get information stored in these symbols written on the paper of the books. So basically symbols are tools which we use to work with information. In computer systems, in digital systems, symbols can be coded, yes, encoded in binary symbols. So for binary symbol, there are only two possible values, yes, the binary symbol 0 or 1. They are logical levels, yes. So yes or no, basically, yes, switch turned on or switch turned off. And each letter in computers is coded in different number of such binary symbols. Well, for now, we can actually say that is equivalent to bit. Yes, basically, this can be seen as one bit. But further, you will know that one binary symbol is not necessarily the same thing as one bit. For example, one symbol, 0 or 1, can have less than one bit of information. And we'll discuss how it can happen. But for now, we can basically say that it's actually a bit. So for ASCII table, as you know, we have 8 bits per character. So basically letter A will have a combination of 8 binary symbols. Yes, zeros and ones. And there are also other encoding tables such as UTF, which uses 16 or maybe even 32. And basically this allows to store larger amount of different symbols, because the limiting factor is how many combinations you can make from 8 bits. From 8 bits you can make starting from 8 zeros, yes, and ending by 8 1 symbols, which gives in total 256 possible combinations, which can be calculated as 2 power of number of bits. Yes, and it's certain that it will be nowhere near enough for all the languages in the world. Yes, basically we have usually in ASCII table some English characters and some local characters. Well, for example, in Latvian we have some diacritical signs, yes, which are added to usual characters, let us say so. And these take up also additional space. In addition to that, we have digits, we have different signs, yes, and a lot of other characters. So all they make up these 256 characters basically for one language. So for UTF, we have total volume of 2 power of 16, which is the square of 256 and somewhere around 16,000. Yes, more actually than that. And this is quite enough to actually put all the information about basically almost all languages. Now, I don't know about maybe some Chinese characters. There may be a lot of these characters, and taking into consideration that we put here Latin symbols, Greek symbols, Cyrillic symbols, and other Chinese, Japanese, Korean, and so on, it may be still not enough, even this number, yes? But it's okay. So basically, symbols can be represented in different forms: as a symbol on paper, as a sequence of binary symbols, yes, code word, let us say so, and so on. Here is example of the ASCII table symbols. Yes, you can see that for the symbol A is capital A. It was actually this binary code. Yes, and you can, if you are interested, follow this link and see this table completely. But it's important to stress out that symbols are not exactly always like letters or digits. They are fragments of information. Yes. So, for example, when we talk over the phone, we can consider separate phrases and words as a symbols, which we send by communication systems. For text, as it was described before, it's letters and digits. For television, it's a separate frame, yes, a picture which is sent. This can be also considered as a symbol. Furthermore, there can be temperature values read from some sensors, pressure, and so on, and mathematical symbols or other special functions, yes. Hard to imagine examples here, but it's possible, yes. For example, integral symbol, yes, or well, this is also a character, sigma, yes, from Greek alphabet. But some specific symbols also can be used as a symbol. So the symbols themselves, however, don't contain, no, they contain some specific information, but another thing is important, how the symbols are arranged into the message. Yes, so basically we use symbols to form some message which is being sent. So what you can see here on the screen is also a message consisting of separate symbols. Yes, and the way I used these symbols to group provides information. You can use, well, we have in English alphabet somewhere around 30 plus letters, yes, and we can use these letters to share any information, yes. So basically the symbols are not changing, yes, the same, but we can group these symbols in many different ways to make different messages containing different information. So we are still talking about something more or less non-material, yes, because the message itself is also some fact, some idea, some news, and so on. We use some material things like paper or flash drive or hard disk drives or screens or something else to show us this message, but the message itself is something non-material, yes. So example is a text consisting of letters and so on. This yes, so this is the example of the message. So now when we need to put that message somewhere, we need the carrier for this message. And the carrier for this message is usually a signal, yes, for our communication systems. So basically, what is signal? A signal is some material, a physically existing process, yes, or some material which is like you know, paper, wood, metal, stone, or anything like that. Some material we use to craft some things. Yes. So this is either material carrier or physical process, which both exist in nature, which can be measured, which can be worked with, which can be felt. Yes. So basically, this way, this process or material repeats in some way the information of a message. So we put our message into this signal. The simple example is electrical signal, rectangular pulses representing zeros and ones. Yes, so this is, for example, voltage, the flow of electrical particles. I mean, the current is flow of electrical particles, and the voltage is change of the potential. Yes, of the charge. Yes, so basically some amplitude plus u and 0, and the symbols themselves are these 1 or 0. And the message is the sequence of these symbols. So we put this message into this signal, which exists in our nature and can be worked with. Yes. So basically, this is how we come to working with information. From this perspective, the paper can also be considered as some sort of a signal. Yes. But of course, in our course, we will talk more about processes. Yes, about physical process, such as, well, actually, it's the next slide, such as waves, current, voltage, yes, optical waves, and all these can be made to actually send some information. For example, we can vary the light brightness, yes, to make it brighter or not so bright according to some law, and this will send some information as an optical wave. Similarly, we can use electromagnetic waves to send this information. As for material carriers, this can be paper, advanced technological devices such as hard drives, USB drives, and so on and so on. And we'll talk about more like physical processes, yes. And more specifically, we'll talk a lot about electromagnetic waves, about voltage or current signals, not so much maybe about acoustic waves. So this will be the signal which we use to actually transmit information. So now we know what is information. Now we know how we can work with this information, and actually we have a good idea of how we can send this information. So we need to generate some signal, and then we can send this signal by using, for example, some wire to some distance. But in order for all of this to happen, we need a system which consists of two parts: a transmitter and receiver. These are parts of the system. This is not a person or device is receiving information, but the elements of a system. Now, for the let us say person or device who needs to send or receive information, there are different terms. Yes, so the sending part is called a source, which generates information, and the receiving part is called destination. Yes, so basically these are not parts of a system. This can be person, this can be other device, computers, and so on and so on. But the source uses transmitter to send over some, let us say, line information to receiver, and destination gets this information from receiver. So obviously, we need some components used together. They need to work together and be compatible with one another. Yes, use some protocols. Yes, specific, which is a set of actions, how these components communicate with each other. Yes, when one component sends information to another, and so on. Some, let us say, rules of operation for these components. And all this protocol and these components themselves accordingly make a telecommunications system. which we'll talk about this during this course. So, as I said, telecommunication system consists of transmitter and a receiver. So for transmitter, this is a set of electronic equipment, yes, related to collecting information, converting this information, processing, and sending it from the source in the channel or lane. Accordingly, this makes some certain operations we'll talk about today. What are those? Like coding, modulating, formatting, and so on. So this is on the one side. Yes, basically, if we watch this diagram, so the transmitter will be here. That is transmitter. For short, it can be denoted as TX. This is usual practice. Yes, and accordingly, the receiver will be this part. Rx. As source and destination are not part of the system and not accordingly part of transmitter or receiver. These are person or other devices. So, receiver is also a set of electronic equipment which also processes signals and information in some way and represents it in the user-friendly form. So we need this destination to actually understand what it receives. Because, well, as you imagine, for example, let us consider what is happening right now. We are having lecture over internet. Yes, we use communication system, which is basically in this case a computer device, or maybe somebody is using mobile device as well. So what happens here is that I am a source and I am using acoustic waves, yes, acoustic waves, to send you some message. This is a signal which is happening. This computer on my side has a microphone which converts this acoustic signal to electrical signal. Furthermore, this electrical signal then is formed as a packets for computer network and sent over the internet. Now, internet connects with different types of wire. Somewhere we have optical cables, somewhere we have Ethernet cables, let's say. So yes, copper wire. And somewhere we have also Wi-Fi, yes, wireless connection. This way, going through all of these, it's eventually coming to your computer or your device, which then processes these packets, plays back by sending electrical signal to your playback device. I don't know, headphones, maybe speakers, yes, which accordingly again generates acoustic waves that you as a person can hear. Acoustic waves. Yes, and this way system works. Yes, so basically that is what is considered this user-friendly form. Yes, because as person here with audio information, we can work only with acoustic waves. We cannot really understand these electrical signals if they are sent, I don't know, onto our skin somehow, or, well, maybe there could be a way if we have some hearing device, and but again, this will change the electrical signal into some mechanical vibrations or something like that, which again is conversion of the type. So the idea is still the same, that we are actually converting the information, converting the processes, yes, from user-friendly to system-friendly, because system can work with digital information, I even didn't currently speak about what each block does, but we'll talk about it on our second lecture today in particular. But you need to understand that here we had acoustic, which are then converted at the beginning into electrical signal. And furthermore, somewhere here, we need to convert this into the digital information consisting of ones and zeros. Yes, this is additional information conversion which is made. And then everything that we watch here, source encoder, intermeter, scrambler, partially also modulator, can be done into a computer chip, some type of the processor or microcontroller. Yes. And this is very convenient because this way it's not important. Is it audio? Is it video? Is it some other form? Is it text? Is it banking information? Everything is sooner or later reduced into this binary form, which can be processed with a computer, with processors of some kind. And it's not even important for system to know what type of information is it. Mostly, yes, because as we'll talk about encoding and decoding, in some particular cases it does matter, but I will mention when we get there in what cases and how. So between our transmitter and receiver, there is a communications channel. Yes, here we have channel. And as I was pointing out in our example right before 5 minutes ago, yes, this channel can be different. It can be wired, it can be cable, it can be optical fiber, it can be air. Yes, it even is possible to send information in complete vacuum in space. So there are different types of channels. Yes, so this is some sort of physical medium or accordingly space. Yes, where signal can be transmitted. Now, of course, the signal needs to be in form capable of being transmitted in this system. For example, we cannot really send acoustical waves into the space because there is no matter, and accordingly the waves cannot happen. Yes, there we need to use, for example, electromagnetic waves or light waves. So this is a physical definition of the channel. There is also a logical definition to channel. So imagine the situation when we have multiple users. For example, mobile communication systems, when you can call one another, yes, and accordingly each user has a part of a system, part of all the well, maybe another example, yes, internet, yes. Imagine we have optical cable, very high speed optical cable connected to some building where we have many users. While it's true that this optical cable is channel itself, also each user has its own channel. So here we have channel 1, here we have channel 2, and they are all only a part of this complete channel. Yes, there can be other buildings as well connected to this very same high-speed optical cable. Yes, and each user takes a part of this channel, some share. Yes, and basically each channel is also called channel. So here we can understand that channels can be merged into other channels. Yes, let us say so, into higher speed channels. So multiple users can use same physical medium simultaneously, and there can be more logical channels at the same time in one cable, for example. Yes, so here, for example, channel 1 is sending information somewhere here. channel 2 is sending information somewhere here, and these two logical channels happen in the same one physical channel. So this also is maybe important thing to consider when you talk about channel. What exactly channel do you mean? So next, channels, transmitters, receivers form a telecommunications network, very similar again to this optical network example, or perhaps mobile phone network. Yes, we have base station, which also has transmitter, receiver, which is connected via optical fiber with other base stations, with control center, control. We have handheld devices, mobile phones, yes, which connect here. And this all makes a network. All of this is actually a network. Well, usually, of course, it has many users, and there is some type of mechanisms used to address users, so that user 1 can send information to user 2 via this network, yes, or to the user 3 or to the user 4. For example, we use telephone numbers in this particular case as addresses. Okay, so yes, before we start talking about specific system, also let's talk what kinds of system can be. So basically, let's see how different these systems can be based on different principles. Based on functionality, we can describe phone networks, television networks, computer networks, because they have different functionality. Here we use it for calls, here we use it to watch television. Computer networks actually can do both of these things and even more, yes. Then we have telemetry networks, some measurements transfer, for example, when we launch space shuttles or something else. All this information about shuttle, about fuel, about anything needs to be sent on the ground, yes. And the same goes for regular airplanes, yes. This is actually some specific functionality which is needed from the system. There is also some telematic systems, yes, which is simple, in simple words, a remote control. Yes, imagine that you have some drone, for example, which you can control from your computer. So this is actually a telematic system which sends information from your computer to the drone. There is also such type as navigation systems which are used to actually understand where are you located in the world, and or in the city or in the country, yes, based on the signal sent from satellites, yes. So on functionality based, the systems can be divided into different types. These systems can be divided into different types also based on the number of channels. So there can be single channel systems, such as some radio systems, yes, where you have these radios with antennas. You press a button, talk, and then your friend has also this radio, and similarly you can communicate. Yes, there is only a single channel and only two of you, for example. Or there can be multiple channel systems, very similar system, which, for example, police or other services use, but they have much more of these radios. They have some central nodes connecting all these radios together, yes, and so on. We'll talk in this course about single channel systems, but it's important to understand that actually it's not that hard. So we have one channel system, we have another one channel system, another one channel system. It's not that hard to actually make a multi-channel system. So we need some mechanism, yes, to merge multiple one-channel system into one, for example, in this case, three-channel system. Yes, and this is called multiplexing. Multiplexing. And that's why we make so much focus on single channel system to understand basics how everything works. And once you know that, by using different multiplexing schemes, we can use time division multiplexing, we can use frequency division multiplexing, we can join multiple single channel systems into one multi-channel system. So it still will work as a single channel system. All the principles will be correct, and you will have a lot of knowledge, enough to understand how multi-channel system works. Based on the type of the signal, they can be analog, yes, continuous, or digital, if the signal is digital, yes, or if the signal is analog. Next, based on error detection, which is true only for digital systems, for analog systems it's impossible to actually do this. There can be different types of systems. So if our system does nothing, not detecting, not correcting any errors, it's one type of system. There is also the system which can only discover that there is actually an error in your message, and in that case, if it finds out that the message is with error, it requires to repeat this message. So we need some feedback channels. So here is transmitter, here is the receiver, here is the channel. Transmitter sends to receiver a message. Message has an error. Receiver discovered that, and by using additional feedback channel, it requests transmitter to send this message again. And there is also a third type of a system which can correct error at once. So it received the message with error, and then it corrects error, yes, itself, without any additional assistance. So for that we use special forward error correction codes. Okay, so this is based on error detection capability. Now, based on direction of message, there are three types of systems. There can be simplex systems, such as usual radio, which we are listening to, such as television, when communications are happening only in one direction. So we have some station, we have radio, and we can only, with our radio, listen to this station. Or GPS system. Yes, your GPS receiver can only receive signals from satellite. It cannot send, nor satellite would be able to receive this signal to the satellite. Yes, so only one directional. Next, we have duplex systems, which can be again divided into two types. Half duplex systems, when we can use the same channel in both directions, but only one per time. Yes, so basically this is again this example with radios. Yes, when you press the button and talk, other person cannot really talk, he listens. Now he listened what you said, you release the button, he pressed the button, and then he talks. So you take turns sending information. You cannot send information simultaneously in both directions. For the full duplex systems, this can actually happen. Yes, you can send information and receive. Basically how our computers work, how our mobile phones work, you can download and upload information at the same time. Yes. And there can be also other criteria, yes, such as channel types, wired or wireless modulation techniques, multiplexing types, how multiple single channel systems are merged into multi-channel regions, so can be local systems, global systems, some area systems, and so on and so on. So now I think we can make a short break of 15 minutes, and then we'll start the second part of our lecture. So thank you for attention and see you again in 15 minutes.